A particularly important form of reaction mechanism that occurs both in nature and in human generated processes is the process of catalysis. This is a way of facilitating a particular reaction in ways that speed it up or cause only a particular reaction out of many possible ones to occur. In this lesson, we're going to be concerned with exactly what is a catalyst and how does it facilitate a chemical reaction. And then toward the end, we'll talk specifically about the ones that we find in our own bodies, enzymes that are present in every cell and facilitate a lot of the reactions that occur in our bodies. So let's start by thinking about what is a catalyst. A catalyst is basically a chemical species that aids a reaction. It facilitates the progress of a reaction so that it happens a little bit faster, and in some cases it causes a particular reaction to happen as opposed to other competing reactions. One thing that's very important about catalysts, though, is that they are not used up in a reaction, so they actually can facilitate many reactions over and over and over again to really facilitate a process. I want to also distinguish these from reaction intermediates. A catalyst is a chemical species that's present both at the start and at the end of a chemical reaction. It doesn't go anywhere. It may be consumed in some ways during the course of reaction, but it's always replenished at the end. An intermediate, in a sense, is almost the opposite. It is not present at the beginning and the end. It's only present somewhere in the middle of the reaction, and it's created during an early reaction or an early reaction step and then destroyed in a later reaction step. Now, we find that there are three principal types of catalysts, at least three principal ones that we'll talk about in this course. The first of these is acid-base catalysis. So we've spent a long time in Module 5 talking about the importance of acid-base chemistry. It turns out in a lot of biological and organic reactions, acids and bases play a role to speed up reactions and even to direct them in certain pathways. A second type of catalysis that we'll be concerned with is so-called heterogeneous surface catalysis. This is a case where reactions take place on a surface, typically a metal surface, and the metal itself actually aids the reaction to happen and provides a template on which the reaction can happen. Of course, the third type of catalyst I mentioned already is enzymes, and these are biological catalysts that aid certain reactions that are critical for life's processes. This leads us to two types of catalyst mechanisms. The first is that the catalyst will form some kind of temporary new bond to a reaction species. It could be a full bond, it could just be a loose intermolecular attraction. But one way or another, by forming that attraction to a reaction species, it alters the species, making it susceptible for reaction. The second mechanism that catalysts can use is to actually just form a template for a reaction. That is, a place where a reaction can take place that either facilitates two reactants coming together. This is typically what happens on a surface, a heterogeneous catalyst. Or it could be actually a well-shaped chamber surrounded by atoms. This is more or less what an enzyme does in cellular reactions. Now, one way to understand what a catalyst does in a reaction is to think about the reaction energy diagrams and how that is represented by a catalyst. These are two different ways that a catalyst might do this, but there is a particular element that's common to both of them. Notice that the energy for activation in both of these diagrams is shown as a very large hill that is measured by energy of activation with a large blue arrow on it. The effect of the catalyst is that it doesn't change where the reactants or the products sit in this energy diagram, but it does change the height of the hill. So it basically reduces the activation energy, and as we know, whenever there's a lower activation energy, that means the reaction can take place faster. Essentially, what the catalyst has done is to create a new pathway, a new mechanism, if you will, that doesn't require as much energy to be put into the reaction system. I think the right-hand side actually draws this more accurately, because typically what a catalyst does by changing the mechanism is it's going to change the pathway by which the reaction takes place. And so by changing the pathway, it's possible that new intermediates would be formed in that. but the net effect is that it will lower the activation energy so that the reaction can take place faster. Now, this table, I apologize, there's a lot of information on this slide. You may want to take a screenshot of this table so that you have it for reference. But I wanted to go through essentially the different ways that these three different catalysts can work. Now, there's going to be several steps that are important and common to all of them. The first, and these are the things marked in the leftmost column. The first of these is the preparation of the reaction. In this sense, the reactants are modified by the catalyst. This is where a catalyst might form a bond to a reactant, or it might interact with the reactant in another way that basically makes it susceptible for undergoing a chemical reaction. The second step is initiation. This is where the two reactants are going to be brought together so that they can undergo a reaction. In the execution stage, that can vary quite a bit depending on the nature of the catalyst. So I'm not even going to try and clarify that, but just say that this is the stage at which the reaction actually occurs. In the fourth step, we have reconstitution. That is, product formation will then restore the catalyst to its initial state so that it can go and work on another type of reaction. So how do these look for these different catalyst types? Well, if we're talking about acid-base catalysts, the first step, the preparation, is that the reactant is protonated, or it has a proton removed. So that alters the reactant in such a way that it's more susceptible to undergo a reaction. In the second step, the reactants then are induced to participate in what amounts to acid-base chemistry. And then once that acid-base chemistry is finished, the initial acid-base reverses. That is to say, the catalyst will then undo what it did in the first step. So if it protonated something, it will take the proton back. If it removed a proton from a reactant, it'll donate the proton back. It reverses that first step so that we are able to recover products. This sort of catalyst is mostly used in organic reactions, although some inorganic reactions as well, used for synthesis of certain chemical species. In the case of metal surface catalysts, this is the blue column, the first step is that the reactant adsorbs onto a metal surface. Now when I say adsorb, all I mean is that the reactant comes down, it hits the surface, and it sticks there. It doesn't get drawn into the solid metal, it just sticks on the surface, and it can move around on the surface. So that's key for the second step, because the second step consists of reactants diffusing or moving around on the surface until they encounter one another. Once they form products, once the reaction has occurred in step 4, they then can desorb, which means they detach themselves from the surface. So it's pretty easy to see how the catalyst is regenerated during this process. The catalyst is always there, and when the products desorb from the surface, it's now once again available for the next set of reactants to come in. This is typically used for gas phase reactions. It can be used in solution phase as well, and it's largely used in industrial production. So chemical industry wants to make a whole bunch of some kind of molecule. It could be a drug. It may use surface catalysts to induce those reactions to happen a little bit more quickly so they can save money. And the third type of reactant catalyst is enzymes, and what tends to happen in enzymes is that they prepare their molecules for reaction by having the reactant bind to what is called an active site on the enzyme. That's a particular place on the enzyme where the reaction can occur. Once it's there, the reactants are brought together at that active site, and that's where the reaction then occurs. Once it is completed, then products detach from that active site of the enzyme, and the enzyme is now ready to catalyze another one of these cellular reactions. So clearly, enzymes are particular for biological reactions, and they certainly are key to certain essential cellular reactions and processes that go on in our bodies. I want to first talk a little bit about metal surface catalysis and give you an example of that. One reason that, or there are several reasons why one might want to use a metal surface catalysis. It certainly can accelerate the reaction. It also means that lower energy is needed to get the reaction to go. If you think about what's happening in an industry, they've got to supply the energy either by heating stuff up or running electricity through it. So if they can lower the energy that's needed, that saves them money. It saves them costs in running the reactions. Another advantage to doing this is that sometimes if the metal catalyst works properly, it can reduce unwanted side products. Oftentimes when you're in an industry situation, there is a particular molecule that you want to make, and if your reaction tends to make a whole bunch of different molecules, it's not very useful for you, because then you've got to purify the result that you get out of the process. In this way, these kinds of catalysts can also reduce waste that's generated. So it's a good sustainable way of helping the environment and helping the industry save money. And as a good example, ethylene hydrogenation takes place often on a surface, in this case a nickel surface. So the nickel is shown in this diagram as a green set of atoms. And what happens first is that hydrogen comes in and adsorbs on the surface. Now what the nickel surface does is it basically breaks that hydrogen molecule into two hydrogen atoms. In a subsequent step, when ethylene, which is C2H4, and has a double bond between the two carbons, when it comes down and attaches itself to the surface actually breaks the double bond between the two carbons. This, in some sense, facilitates the reaction that's going to happen. Because what will ultimately happen is those hydrogen atoms will move around on the surface of the nickel. They will come close to the ethylene, and they will actually attach one to each of the carbons on the ethylene, forming ethane. Once it forms ethane, the ethane desorbs from the nickel surface, and we have basically the completed reaction. So this is a way of taking ethylene, C2H4, to ethane, which is C2H6. We're adding hydrogen to it. You may also be aware, or maybe not, that the Haber process for ammonia synthesis also requires a catalyst. And in this case, this is both a facilitation and a cost-saving measure. The Haber reaction is just nitrogen reacting with hydrogen to make ammonia. It is an exothermic reaction with a delta H of minus 92 kilojoules per mole. There are two issues that industry would like to optimize. First, they want to shift the equilibrium so that it favors products as much as possible. They want to make ammonia from nitrogen and hydrogen. They also would like the reaction to happen quickly. They don't want this to hang around for years and years to take place. They want to get past a very large energy barrier, because remember, that nitrogen-nitrogen bond is very strong. It takes a lot of energy to get that to break so that you can make the ammonia. So these are the issues that industry might face with this. Now, one possibility would be to increase the temperature of the reaction, but this has several effects. It will increase the collision frequency. This is a gas phase reaction. It'll increase the collision energy, so that's all to the good. But notice that because it's an exothermic reaction, Le Chatelier's principle tells us that increasing the temperature actually favors reactants, not products. There are more molecules in the gas phase there, so increasing the pressure would actually force it to the right. So you have two possibilities. You can raise the temperature, which shifts things to the left, or you can increase the pressure, which shifts them to the right. But there's a limit to how much you can increase the pressure. So what do? How do you fix this? Well, there's actually a compromise that's done. We do raise the temperature, so to 400 to 450 degrees centigrade, which, remember, in Kelvin is 673 to 723. We also increase the pressure to 200 atmospheres. That's a huge pressure, and it is very expensive for industries to impose this pressure, but it would be even more expensive if they had to raise it even higher. Finally, they add a catalyst. They use iron, and iron is pre-treated with potassium hydroxide, which makes it capable of catalyzing this reaction. But it's only under these conditions that you can get a substantial yield of ammonia at conditions that sound extreme, 400 degrees centigrade and 200 atmospheres, but in fact are about as best as you can do under these circumstances. Let's talk for a few minutes about enzyme catalysis. So what is an enzyme? We talked about this a little bit in Chemistry 1083. It's a protein. It can be a nucleic acid, in which case it's called a ribozyme, but it facilitates cellular reactions. And as a protein, I hope you remember that proteins are large polypeptide chains that take on a certain shape. In fact, the shape is very specific to proteins, and they facilitate chemical reactions once they have both formed the polypeptide chain and then assumed the shape. So let's talk about some basic features. First of all, almost all your cellular reactions are mediated by an enzyme of one form or another. They are usually usually tailored to catalyze a particular substrate, that is a particular reactant molecule. So once you have an enzyme, it can help the reactions of one molecule but not another molecule. That's facilitated by a different enzyme. So these are really very specific tools that the cell uses to facilitate your reactions. They can only facilitate one type of reaction. So for example, an enzyme for a given molecule might help break one of its bonds. And usually those enzymes end with the word LASE or the suffix LASE. So, some kind of acetylase or something. Although these are macromolecules, their active site, and I mentioned that earlier with enzymes, their active site is actually quite small. It's very specific, and it's tailored to only fit a particular molecule. That's how it can be specific to a particular substrate. Many of these enzymes use a metal at the active site. Now, this is not a metal surface. This is a metal atom that is embedded somewhere in the protein or in the enzyme. So you might hear also the words metallopropene or metalloprotein or metalloenzyme used to describe these things. They are enzymes or proteins that have a metal embedded in them that helps their functionality. That metal is usually at the active site. And as I mentioned earlier, the shape of the protein enzyme is very important to its function. Moreover, that shape is sensitive to temperature and to the acidity of the environment. So if either of those things change, it can cause the enzyme to become deactivated, so it no longer works properly. So we find that there's a lot of stuff in nature and a lot of stuff in biology that requires very specific conditions, and it's been tailored beautifully to match those conditions so that the reactions take place properly. Now, as for the mechanism that enzymes use, I'm showing you sort of a complex presentation of that. They're basically believed to be, for most enzyme reactions, two steps, so it's a two-step mechanism. In the first step, the enzyme, which is represented by E, and the substrate, that's the reactant that's going to undergo the reaction, is represented by S. Essentially what happens is they form an equilibrium where the substrate is attached to the enzyme, that it basically attaches at the active site. So the forward rate would just have a rate of K1 times the concentration of the enzyme times the concentration of the substrate. The reverse rate would be K minus 1 times the concentration of the enzyme substrate complex. All right, so it's useful to think of this as that you've got a limited number of enzymes there, and you've got a bunch of substrate around it. And those substrate molecules can come in and they can attach for a while to an enzyme, and they may undergo a reaction, or they may not. They may detach themselves from the enzyme before they undergo a reaction. All right, but for this to be a successful operation, there's got to be enough of them that do undergo a reaction. So that's what happens in step 2. In step 2, that enzyme substrate complex will form products, and then the products will separate from the enzyme. So the products are represented by the letter P. The rate for this step, which is usually the rate determining step in this, I say usually, but could be the other one, but usually this one, would be given by K2 times the enzyme substrate complex. So the net reaction is basically an enzyme combines with a substrate to form the enzyme again and the products. And the enzyme is essentially unchanged by this reaction. Now, I've got a picture over the side taken from the internet that shows you sort of what this might look like in a cartoon. Okay, the substrate is represented by the dark blue thing with the funny shape. The enzyme is the light blue thing that has a hole in it that's just the right shape to fit the substrate. So the substrate will come in and it will bind to the enzyme. And in fact, what happens is that both of them adjust a little bit to tune that fit so that it works just right, and that's called the induced fit model. Once the reaction has occurred, and products are now shown as green and orange, they separate from the enzyme and they go off and do the next step in their lifetime. So the two steps that appear in the mechanism are labeled there. Step 1 is basically going from the first part of the cartoon to the second, and step 2 is going from the second part of the cartoon to the third. Now, this particular mechanism was studied extensively in the 1920s by a pair of biochemists named Michaelis and Menton. And they studied and basically characterized this dynamics quite a bit and wrote down a rate law for it, which is still called the Michaelis-Menten equation for the rate of enzyme catalysis, still used today. So I hope we've learned a little bit about catalysis and how it facilitates chemical reactions, and more specifically, how enzymes do that in our cells. Thank you.